Okay, for this time, for real, welcome back to the second lecture of the two lectures we have on probability and statistics as a part of the ACM Summer School in Data Science at Goa University. So, again, we were going to talk to you. First lecture was on basic probability theory. Today, we're going to talk about descriptive and inferential statistics. And what you're going to realize is that these are really two sides of the same coin. We're essentially talking about the same phenomena, which is the probabilistic framework. In the first lecture, we were concerned with describing the phenomena and trying to figure out the likelihood of various events. Right? So you would say the phenomena is this is the random variable. And then we said, what is the probability of this outcome happening? What is the probability of these outcomes happening? Now, we're going to take the same paradigm. Right? You have this phenomena that's generating outcomes in a probabilistic framework, the same random experiments, same random variables. But what we're going to be interested in is the outcomes. So we're going to tell you that these are the outcomes. And now you characterize the outcomes or make inferences about the phenomena that could have generated this outcome. So essentially, you're dealing with the same construct. What you're given and what you're trying to figure out is what is really changing. Right? Okay, so now it's at the very outset, I just want to kind of define for you descriptive and inferential statistics and how they're different and where what is applicable and so on. So the first thing is, so descriptive statistics does not mean just generally describing the data. It's a quantitative framework. You're going to quantitatively or graphically describe the data, but when you're given a piece of data, descriptive statistics confines itself to that data. So either you summarize the data through a chart, or you summarize the data through some measures of central tendency or variability. You plot the data in some way. The data is kind of like the end-all and be-all of the whole story. So you take the data and you represent it. That's your descriptive statistics. With inferential statistics, you're doing something very different. You're first of all, you're going back to this probabilistic framework, where you remember how you had this random variable and you had variates? You go back to that and you're saying, what I have, so there are two ways of thinking about it. I'll talk about the two different ways. One is to think of this notion of there being a large data set, which is a population. And what you have is a subset. Okay, so that's one paradigm. Now, the second paradigm is to go to this random variable and variates. You're not really talking about a large data set, but you have a random variable. What you're getting is some variates. In both cases, you realize that what you have in your hand, which is this subset of data, is not the end-all and be-all of the story. It's either a subset from a population, which is a much larger data set. That's one way of thinking about it. Or the other is, forget about this larger data set and so on. What you had was a random variable. The random variable was the truth. What you're interested in is the random variable. What you have are some variates. In both cases, you're interested in something bigger, something that is the backdrop from which this got created. And in a lot of such instances, you're not very happy. It's not that very useful to just characterize this data. You want to talk about the population from which this data came. Right? You have a sample. The sample was taken from a population. It's useless to say in this sample the mean is 2.5. I'm interested in what that population's mean would have been. I unfortunately don't have it. Right? I had a random variable. That random variable gave me some variates. Right? I can tell you that these variates, these 10 data points, these 20 data points that I have, the mean of these 20 data points is 7.4. But I'm more interested in what the mean of that random variable that created these variates are. So that's where you're going to use inferential statistics. Right? In the end of the day, you don't have the population, you don't have the truth about what it is that is creating these variates. But you want to make a statement about that. Okay? You want to use these samples to make a statement about that. So in a sense, when you take a piece of data and you characterize only that data, you're dealing with descriptive statistics. With inferential statistics, you're going into this paradigm saying that this data set is but a sample from a population, or these are just a sample drawn from some random variable. What can I say about the random variable? What can I say about the population with just this piece of information? Okay, so let me very quickly see, even something like descriptive statistics can be spread across, as an entire course. Graphical techniques have become so advanced that it's really worth dwelling on them. I'm just going to give you a very 2 to 3 minute overview of just trying to give you a glimpse of what is there to be covered. Broadly, descriptive statistics are broken down into graphical techniques and numerical summary. So you can graphically summarize the data, you can numerically summarize the data. Sometimes it's in the form of summary statistics, and sometimes it's in the form of tables, right? So we're going to spend a few minutes just talking about descriptive statistics, and then we're going to jump over to inferential statistics. Okay. So it turns out that if you want to describe data, it really matters what kind of data it is. So data, many of you might have come across this paradigm of nominal, ordinal, interval, ratio, qualitative, quantitative, continuous, discrete, and each of these definitions will kind of overlap with some other of these definitions. But keeping it quite straightforward, if you have a qualitative variable, you want to graphically represent it, the bar graph and pie chart are two very common ways of doing so. And even there, the only reason I kind of highlight such examples is, again, even here the nuance matters. For instance, if your variable was ordinal and qualitative, which one of these two would you prefer? Does everybody know what ordinal means? So can you give me an example of something that is ordinal and qualitative? Marks of students could be quantitative, right? Because it can be a number. So for it to be qualitative, it might have to, take on. Gold, silver, bronze is a standard example. Young, adult, old. Again, you could make an argument saying that that is a mapping of a quantitative variable onto a qualitative. In some cases, that's what happens. I mean, often credit scores and so on, they're computed very rigorously quantitatively, and then they're given an A star, or AAA, or whatever. Sometimes that happens. Sometimes the mapping does not make sense. Gold, silver, bronze, for instance, does not. Terror, threat level, orange, yellow, green, red, or whatever, it probably does not. Sometimes even something like, while you can think of it as first mark, second mark, and third mark, although it's 1, 2, and 3, in a certain paradigm, you can think of it as essentially a qualitative variable, because all you're saying is the person who came first is called the first, right? I could have replaced that with ABC in some sense. But in all the examples that I've given you qualitative variables where there was an order. Red, green, orange, or whatever, right? So there, would you prefer the bar graph or the pie chart? Okay, to help you with this, let's contrast it to maybe a qualitative variable where there was no order, right? So suppose the color of the dress that's chosen is a variable. It's a qualitative variable, and it can take any possible, this thing. So there you would prefer a pie chart, right? Because you're not trying to express any order in that qualitative variable. Here, for instance, I've chosen some disciplines in an engineering department. And this is basically just the count of them. So number of people in mechanical, number of people in computer science. And here you don't want to in any way signify that one is moving in any direction. Whereas if I take something like level of education, which I'm describing as an ordinal qualitative variable, I really like the order. There is an order. There's a reason bachelor's is between high school and master's, and there's a reason that master's is between bachelor's and doctorate. So I think my point is not to have a complete enumeration of all the graphical techniques that are available, but thinking through, the story you tell greatly depends on the kind of variable you have and the medium that you're going to choose to express it in. Okay. For quantitative variables, again, you have various tools and techniques. If you have a single quantitative variable, something that's very convenient is a box plot. A box plot, basically, again, our tutorial sessions, we will have you actually plot some of these things and so on, so you get used to it. But a box plot is capable of capturing many aspects of a variable, a quantitative variable. For instance, the central tendency is often captured through the median, which you see as a red line in between. The box beginning and end, let me get my pen out. The box beginning and end that's here and here typically are the first and the third quartiles, right? And what we mean by that is the 25th percentile and the 75th percentile. Usually you have these things called whiskers that go all the way till here and here, and those are typically the minimum and the maximum. And usually when you have a data point that's what we would like to call an outlier or just completely out of the range, we don't go all the way. We don't let the whiskers go all the way. You have different heuristics. One of them is to use 1.5 times the interquartile range. So this range is called the interquartile range. And you go 1.5 times the interquartile range above the upper quartile, and that's your ceiling. So any point above that is called an outlier, and then you look downwards and find the next highest point, and that's your max. That's where the whisker ends. The same logic would apply to the bottom, right? So look at all the things that this has actually captured. This has captured some notion of centrality. This, through the max, min, as well as the interquartile range, has captured some notion of spread. Pretty soon we're going to discuss how it also captures certain other phenomena associated with random variables. We're going to define something called skew and kurtosis, and you'll see how box plots, in a way, also capture those two quantities. When you have more than one variable, if both of these are continuous, right, you like a scatter plot if it's a continuous quantitative variable. If you have one variable that's continuous and you want to look at it across some categorical variable, sometimes you can have multiple box plots. That's what I've shown out here. And finally, if both your variables are really just qualitative, but you want to get a notion of how they are codependent and so on, a contingency table works very well. Okay, so this is just a very quick summary of graphical representations. Many times in descriptive statistics, what you want to do is summarize the data through numbers, right? And here we've broadly spoken about measures of central tendency. That's things like mean, median, mode, right? Dispersion. Dispersion is usually characterized through things like standard deviation, which is nothing but the square root of variance, mean absolute deviation. So one argument is as follows, right? If you want to look at the deviation if you want to get an idea of the spread of numbers, what you did was you took each number and looked at its distance from the mean and squared it. Now, what was the rationale behind squaring it? You said, well, I'm trying to just capture the magnitude of how far numbers deviate. I'm not really interested in the signs. One convenient way of getting rid of the signs is just to square it. And that was extremely convenient back in the day when, taking the modulus or absolute value meant you could not do further things mathematically, like differentiate and so on. So people really loved this way of getting rid of the signs. But now, it's perfectly normal to define some measure of dispersion, which is just losing the sign. I'm just going to take the absolute value of the deviation of each data point to the mean and take the average of all of those. Right? Just forget about the sign. That gives you another measure of dispersion, and that measure is going to be different from standard deviation. You also have two other aspects that you want to characterize. So when I'm talking about summarizing data through numbers, right? All along the way, I'm telling you, think of that random variable. Think of that distribution. So the ultimate way you would want to characterize the random variable is through the distribution itself, is through defining that mathematical function, right? But what you're left with sometimes is just the data. And with the data, you might not, it's 2 to 3 steps before you actually characterize the random variable, right? You have to fit distributions and then figure out. So graphically, you can create a histogram. Numerically, a convenient summary of the distribution can be got through the mean, the standard deviation. And you have two other phenomena called skew and kurtosis. Again, people like to characterize it through first moment, second moment, third, and fourth. Here, I'm just going to try and give you a very quick intuition for it. So you already have an intuition for the mean and variance. One tells you where things are centered, other tells you how things are spread. Even for the same spread, right? Skew captures how it can be asymmetric. So if this is the mean, is it spreading equally on this side as well as this side? Or is it, you can still have that average deviation being equal to some value x, but it's not symmetrically deviating on both sides of the mean, right? And that is captured. The degree of asymmetry is in some sense captured by skew. And kurtosis, I'm going to give you a very informal, non-statistical intuition for it, which will make any statistician or mathematician curl up. But think of it this way, right? So imagine two different, forget about the asymmetry. Everything is symmetric. Let's start there. Now, the standard deviation is some notion of average deviation, correct? You take each point, see how much is deviating, and you're taking some notion of average, right? Now, can two different distributions have the same average deviation, but have different standard deviations of the deviation? It's a very messy thing to think about, right? So think that there are two completely different distributions, okay? Both of them are on average having the same deviation of the data points from the mean. But in distribution 1, every point is deviating from the mean by exactly the same amount. So that means obviously half of them are deviating on the plus side, half are deviating on the minus side, but they're all deviating from the mean by the exact same amount. And therefore, that's the average deviation. In the other distribution, some points are not deviating from the mean at all. They're all sitting on the mean. The other points are compensating for them and deviating a lot from the mean. Both these guys have the same average deviation of points from the mean, and therefore they both have the same variance. But they have very different kurtosis. The one that has a lot of kurtosis is the one that has a lot of variability in the deviation of the points from the mean, whereas the other one is more consistent in that sense. So this is definitely, I know it's being recorded, but definitely not the formal definition, but I hope it gives you some feel for what really kurtosis is. Okay, so very quickly, you already are aware of everything to the right side of the screen, right? So we've already been discussing this. So for the discrete case, you know what the expected value is. Here I'm making a small deviation. I'm not using minus infinity to plus infinity. I'm just using this notion that A to B means A is the lowest point in the distribution, B is the highest point in the distribution. We know how expected value is nothing but xi times, I've written pi here, but that's essentially f of xi, right, which is the PMF of the function. So it's the same idea. Now, I've put this in the same table versus something to the left, which is what we are going to be primarily interested in. So when we talk about mean and standard deviation in statistics, you're really talking about the arithmetic mean. Empirically, how do you compute mean and standard deviation? So theoretically, if I gave you a random variable, what were you doing? You were taking each possible outcome and weighting it by the likelihood of that outcome, correct? Here, you're given none of that. You're just given a data set. So what are you going to do? You're just going to take all the numbers, add them up, and divide by n. So the same, again, idea applies to standard deviation. Of course, we have this subtle difference that if you're using x bar, right, this is often referred to as sample standard deviation versus population standard deviation, you will be dividing by n minus 1, right? And the idea is fairly straightforward. The idea is you have a data set, and in that what standard deviation claimed to do was measure in an unbiased way the deviation of each data point from the mean. The problem is you don't know the mean, right? And you're computing the mean. So if you knew the mean, and if God dropped mean for you from the sky, and somebody told you that was mu, and I'm being facetious here, there are some real world situations where you'll know the mean, but you want to reassess the standard deviation. Sometimes a process goes through a change, something that you're measuring goes through a change, where you can, in principle, say the mean really should not have changed. So you actually do know the mean from another source of data or from some long-term history, in which case you're very fine, you're comfortable using mu as it is. But there, despite the fact that you're using a finite number of data points to compute standard deviation, you use 1 by n. Because the mean that you're using to measure the deviation of each data point did not come from that same data set. However, if you're using what I call as x bar, which is nothing but the arithmetic mean of those data points, and you're using that as a proxy for the true mean, you need to adjust for it by n minus 1. And I'm not going to print it to give you the full, it's called Bessel's correction, the full correction, but I'm going to give you maybe a 30-second intuition for it. The intuition is as follows. Is x bar guaranteed to be mu? No. But is x bar equally likely to deviate from mu on either side? Possibly. It's an unbiased estimate of mu. So while x bar is not a bad idea to use, the problem it turns out is if x bar is going to deviate from mu, it's going to deviate in the direction which is going to find itself conveniently in the middle of the x's. So x's are coming from some random process with some mu in the center. Now x's can sometimes be on the right side, but if x's are on the right side, where is x bar going to be? Conveniently in the middle of it. If x's wind up being on the left side, which is on the lower side, where is x bar? So x bar has this tendency of whether you get lucky or unlucky in terms of dispersion. That's unbiased. Sometimes all the points are going to come together, sometimes all the points. I have to live with that, right? Because I am only given a sample and I have to estimate the standard deviation. But on top of that problem, I'm given this other problem where my x bar is always going to wind up trying to be closer to my x's than what mu would have been. So you're always going to be underestimating if you use 1 by n. So you try to correct for it, and it turns out that the exact correction is the 1 by n minus 1, and there's a very neat derivation that actually shows that. So that's the reason that you do this correction, but hopefully that also tells you in some of these slightly more complicated situations where you use 1 by n minus 1 and where you use 1 by n should hopefully be clear. Okay? Okay. Okay. We're done and dusted with descriptive statistics. We've looked at it from a graphical perspective. We've looked at it from a numerical perspective also, right? Okay, now let's go back to the difference between descriptive and inferential, right? We said in inferential statistics, what we were interested in is in making some inference about the population, and often you're going to find out that we're going to make some inference about the population parameter. So if there is a random variable and it has some mean mu, and some standard deviation sigma, and perhaps some max value, some min value, some median, some 75th percentile, some skew, some kurtosis. These are all parameters, right? Now, what you are getting is a sample. Now, the sample, you can get those parameters from, you can get some estimates of various things from the sample. But we want to make inferences about the population parameters. So you want to say something about mu from the x bar that you're going to get. Okay, you want to say something about the sigma from the S you're going to get. Now, I know I didn't formally introduce it to you with the assumption that you know it. Mu and sigma are used to refer to the populations parameter, whereas x bar and S are used to refer to that sample. For that sample, if I take the mean, that's called x bar. That's not called mu. Mu is the random variable, right, parameter. Okay. So you're going to try and do two kinds of things. Broadly, these are the two kinds of things that you'll be doing. Given a sample statistic like x bar, right, what can I say about the population parameter mu? I always want to say, if I just reported x bar to you, what have I done? Descriptive statistics. But if I want to use that x bar in some way to say something about mu, I'm going to do inferential, and there are two kinds of things I can say. For instance, I can try to tell you with a certain level of confidence where should mu lie. We've all already agreed that x bar is not guaranteed to be equal to mu. But given a particular value of x bars are very easy to get. I can take a sample and I can compute the arithmetic mean. But given the value of x bar, can I tell you where mu should kind of lie with certain confidence? The other thing that I can do is, given a sample, I can answer some pointed questions. Like I can make a hypothesis that mu must be equal to something. So I'll say mu must be equal to 10, or what I hypothesize that mu is equal to 10. Now, given the data that I'm seeing, what I'm going to compute an x bar, and I'm going to do all of that, and I'm going to say, what's the probability that I could have gotten this data if mu was equal to 10? Now, I'm going to belabor this point multiple times through the course, and I might as well start right now. Remember, I'm not telling you what is the probability that mu is equal to 10. I'm not telling you the probability of the hypothesis given the data. That is a Bayesian framework. That's not what we're doing here. We're trying to tell you the probability of the data given the hypothesis, right? And that's what we're doing. We're trying to say, if I hypothesize, if the hypothesis was true that mu was equal to 10, what's the probability of seeing this kind of data? With the idea that if the odds of seeing this kind of data is extremely low, then probably that hypothesis was wrong. But I'm not directly computing the probability of the hypothesis. Right? So it's a little kind of convoluted way of touching your nose, but get used to it, because this is where the mistake is often made in understanding inferential statistics. And now, I do want to touch upon some example of where these get used regularly in data science. Right? So anything that is subject to a window into reality needs to go through the scrutiny of the statistical inference. So very often you might try and use a particular machine learning algorithm on 10 different data sets and get 10 different performance measures. You'll still need some statistical way of saying, I am better, this method is better than that method, right? You might have tried 2 different parameters on a particular algorithm on, on the same data set, but with different thresholds and so on. If you're comparing 2 things, if you're making a conjecture that you made an improvement, all of this, you're getting nothing but, you're not knowing the reality that's underneath, whether you're truly better or not. What you're getting is some glimpse of it in the form of running it on 10 data set, running it on 10 different settings, running it on 5 different machines. If you're looking at computational time of a particular algorithm, each run is not going to be exactly the same as the previous, but you're getting some variates. You are not interested in saying that 10 times I ran this program, this algorithm was faster than that. You want to make a statement that in general, this algorithm is faster than that, right? So you need to do this business of statistical inference. Every time you report any kind of result, right? People are interested in error bars, which is, what is the uncertainty? You've reported to me some X bar. But what is the uncertainty in that X bar that you reported? I want to know within what range mu can exist. And here the mu and X bar are not just 10 cows or 10 donkeys. They're often related to some of the computations or calculations that you're doing in a machine learning context. Okay.